Hello everybody, Mr. Hasty here. Today we're going to be doing our last section, which is 13.3 on gas stoichiometry. So we're going to do a real quick review of the concept of stoichiometry, and then we're going to move into talking about doing it specifically with gases, which is going to allow us to have a new approach. So if you remember, we did our stoichiometry using something called the box label method. It looks like this. And usually what we do is we'd start out with grams of substance A. We would do a conversion, grams of substance A to moles of substance A. And to do that, we'd use a molar mass. That molar mass would come from the periodic table. Remember, to get a molar mass, if it's a single element, you just take the mass number of that element. If it is a compound, like CO2, you would add up 1 carbon and 2 oxygens. Then we would have to convert moles of A to moles of B. You would do that by using a balanced equation. For instance, your equation might say that 2A plus 3B yields, let's say it yields 1A to B3. Well, in this case, your ratio would be 2 to 3 using the coefficients of the worked out simplified equation. Finally, typically you want your answer in grams of B, so we'd use another molar mass to get from moles of B to grams of B. Now, this is a little bit different now because now we can do things in terms of volumes, right? So there is a way to convert volumes into moles. And that is by using the fact that 1 mole of a gas is equal to 22.4 liters of that gas. So now we can do some things going from volume to volume, or mass to volume, or volume to mass. So this is going to make our path a little bit trickier. So let's say we wanted to go from volume to volume. If we start with liters of A, we can convert liters of A to moles of A, and then pretty much using this fixed constant ratio, do the same conversion in the middle where we go from moles of A to moles to B. You'll still need a worked out balanced equation. And then to go from moles of B to liters of B, we could do moles of B to liters of B, just like using the same 1 mole is 22.4 liters. Now, there is actually a shortcut for these specific types of problems. However, we could also choose to stop midway through this and then convert to grams at the end. And we're going to see examples of both of those. So let's look at a couple of examples. So, number 1, what volume of oxygen gas would you need to combine with 2.50 liters of methane in a combustion reaction? So there's a lot of assumptions here. So first of all, it assumes you know what a combustion reaction is. You know what methane is, those things. So first of all, we know what oxygen gas is. Oxygen gas is O2, and we need a balanced equation, so we're going to start there. We have to remember what methane is. Methane is C2H4. And it assumes you know what's going to happen at a combustion reaction. In a combustion reaction, we're going to get water vapor and carbon dioxide. Now we could put all the indicators of gas and liquid here, but actually all of these end up being gases because the water is heated up to a point where it's going to be vapor there. So now we have to balance this equation. Well, let's start with C. Here we have 2 C's on the left and we have 1 C on the right. I'm going to double my C's on the right. So we got, now that C is balanced, the carbon is balanced. Let's check on oxygen. Well, we have 2 oxygen on the left, but we have 4 oxygen, actually 5 oxygen because of that on the right. So the oxygen's not balanced. Also, the hydrogen is not balanced. We have 4 hydrogen on the left and 2 hydrogen on the right. So let's double the hydrogen on the right. Now we've got 4 hydrogen on the right, 4 hydrogen on the left. Let's tackle that oxygen. On the right, we have 4 oxygens in the carbon dioxide and 2 oxygens in the water, so that'd be a total of 6 oxygens, which means we need 3 O2s to get 6 oxygens. So we're going from a volume of oxygen starting from a volume of methane. So we're going to start with 2.50 liters of C2H4. Now, according to the conversion we learned, 22.4 liters of any gas is 1 mole. And here's where the ratio comes in. Basically, there's a 1 here, so 1 mole of C2H4 is going to combine with 3 moles of oxygen. And we want to know the volume, so we use that same ratio. 1 mole of O2 is going to be 22.4 liters of O2. So we're going to talk about a shortcut here in a second, but let's just work this out. Remember, you multiply everything on top, divide by everything on bottom. And I get, without rounding, 7.5, but to maintain sig figs, we'll say 7.50 liters of O2. And here's where the shortcut's going to come in. Some of you might notice that 2.5 times 3 is 7.5. It's because when you're doing a volume-to-volume problem, remember, this only works from volume to volume, you can cancel the 22.4 on top and the 22.4 on bottom, just like we cancel our units when we typically do this type of method. Those will cancel. So really all you have to do is take the volume of the gas you know times the appropriate ratio. And that's a shortcut you could use. So let's do this next problem both ways real quick. So I'm going to start with the shortcut. What volume of carbon dioxide would be produced in that reaction? So we're going to start with 2.5 liters of methane, 2.50 liters of methane. And according to my ratios here, I theoretically should just be able to multiply that. Let's see. Carbon dioxide there's 2 carbon dioxide for every 1 methane. So I should be able to double it. I should get 5.00 as my shortcut. But let's go through the process. 22.4 liters of C2H4, because any gas has this according to Avogadro's principle. And then according to this, 1 mole of C2H4 is 2 moles of CO2 being produced. And then we just need to know that 1 mole of CO2, and again we use Avogadro's principle for this, is 22.4 liters of CO2. And when you work that out, you will indeed get 5.00 liters of CO2. So shortcut or long method doesn't matter to me. If you're very comfortable with the long method, go ahead and do that. If you really understand, oh, well, this is always going to cancel out, okay, you can go ahead and use the shortcut and it won't ever be wrong. All right, let's talk about volume to mass and mass to volume now. All right. Mass to volume or volume mass. So a 13.5 gram sample of aluminum reacts with an excess of hydrochloric acid to form aluminum chloride and hydrogen gas. What volume of hydrogen gas is produced? So we start off with a mass and we want to know a volume. So I'm going to work out my equation here. I'm taking aluminum, which is just aluminum metal, and it reacts with hydrochloric acid. We learned hydrochloric acid is HCl. It's going to yield aluminum chloride. Now, let's think about that. That's an ionic compound. Aluminum's a +3, and chlorine is a -1, so that's going to be AlCl3. Plus hydrogen gas. Remember, gaseous forms of most gases that are not noble is a 2, H2, F2, Cl2, so on. So we have to balance this guy. Well, we obviously have 3 chlorines here on the right side, so we'll need at least 3 chlorines on the right. That looks very messy. Let's clean that up. Chlorine. Now, if we made it 3, we're going to run into a problem because we're going to have 3 hydrogens and we have 2 hydrogens on the right. So we need it to be an even number. If we're talking 3 and we're talking 2, I'm going to give myself 6 hydrogen chlorides. That way, I can get double this here and get my 6 chlorine, triple this here, get my 6 hydrogen. But I need to make sure to balance out that aluminum. So I have 2 aluminum, 6 hydrogen chlorides, yields 2 AlCl3 plus 3 H2. So let's start on our journey here. So basically, one of the reasons we learn the mole concept is because it doesn't matter if we're dealing with mass or gas volumes, we can always go back to the mole concept. So if we have 13.5 grams of aluminum, let's convert that to moles. So how do we do that? Well, we can look on the periodic table and find out that 1 mole of aluminum is 26.982 grams. And that's just the mass number off the periodic table. So now we want to go from moles of aluminum, because we've canceled out our grams here. That should be Al. Moles to moles. From moles to aluminum to moles to hydrogen gas. So we use our worked out formula. It says 2 moles of aluminum will make 3 moles of H2. But we don't want moles of H2, we want liters. And so we can use Avogadro's principle. 1 mole of H2 of any gas is 22.4 liters of that gas. So we just do our conversions on a calculator and we get to, let's see, 3 sig figs, 16.8 liters of hydrogen gas. So now that was going from a mass to a volume, right? We started with a mass, we ended up with a volume. We can go the other way. We can take a volume and go to a mass. So a 7.50 liter sample of acetylene. Now acetylene is C3H8. Sorry, C2H2. Is ignited with oxygen. So we have C2H2 being combined with some oxygen, which is O2, to form carbon dioxide and water, another classic hydrocarbon reaction. So let's balance this. We have 2 carbons on the right. We have 2 carbons on the left, 1 on the right. So we need to double my carbon here. Always try to take care of oxygen last. We have 2 hydrogen and 2 hydrogens, so that looks good. But we run into a problem. Because on the left side we have an even number of oxygen, on the right side we have to have an even number of oxygen. So I'm going to have to go through the following process. So I have to double this, which means I need 4 hydrogens. So that means I have to double this, which means I got to go back and correct this one because it has the wrong number of oxygen. So it's going to be 4 actually. I'm going to clean that up. All right, clean that up. So now I have 4 carbon on the left, 4 carbon on the right, 4 hydrogen left, 4 hydrogen right. Now I have 4 times 2 is 8, plus the 2 from the water is 10, so that's going to be a 5O2. So there's our balanced chemical equation. So we start with 7.50 liters of acetylene, and we can use Avogadro's principle here that 22.4 liters of any gas is 1 mole. Now we have to use the ratio if we're trying to figure out the water. So let's see, in our worked out chemical equation, 2 moles of C2H2 gave us 2 moles of water. And it doesn't want because the water vapor would be a gas initially, but it says it wants condensed down, so it wants it as a mass. So we have to do a molar mass, which means on your periodic table, you're going to add up 1 oxygen with 2 hydrogens, and you would get 18.015 grams of water. So we go ahead and we do that multiplication, and we get 6.0, well, let's see, 3 sig figs here, 6.03 grams of water. All right. I want to thank you guys for this being a great class. This is our last section. We'll be doing a review assignment on this, as well as the other material from the section, and then it'll be quiz time, and that'll be the end of the semester. So again, thank you guys, and I hope to see you after summer break. Bye.